Welcome to this explainer. Today, we're diving straight into a wild intersection of biology, chemistry, and next-gen tech. We're going to look at how scientists are literally using the hidden visual world of bees to solve one of the biggest impending crises in modern computing. I know it sounds straight out of science fiction, but it's very real. And the implications? They're absolutely massive. So let's talk about the physical limits of traditional silicon chips. We are rapidly hitting a wall, what scientists call the electronic bottleneck. For decades, we've made computers faster by shrinking components and packing them tighter and tighter onto a single chip. But there's a literal physical limit here. When you cram that many components together, the movement of electrons creates intense physical friction. If we make them any smaller, these chips will literally melt themselves down or just completely lose data. So yeah, we need a fundamental shift. Here's our roadmap for today's explainer. We'll start with the electronic bottleneck, move into computing with light, then break down the BiOI TiO2 breakthrough, check out 5 gates on one device, and finally, my absolute favorite part, seeing like a bee.
All right, part 1, the electronic bottleneck.
So traditional electronic logic gates have this fatal flaw. They generate something called Joule heating. Since they rely on electrons literally bumping into each other as they travel down a wire, they hit a ton of physical resistance, and that resistance creates excessive damaging heat. Plus, their bandwidth and speed are capped by that clunky movement. The fix? Optoelectronic logic gates. These are systems powered by photons, light. Because photons don't carry mass or charge like electrons do, they can operate at staggering speeds and zip through medium smoothly without generating all that destructive heat. It opens up massive bandwidth capacity. Which brings us right to part 2, computing with light. Before we get bogged down in the complex material science, let's clearly define what we're actually talking about here. An optoelectronic logic gate device, or OELGD for short, is the hero of this explainer. In the simplest terms, instead of sending electrical currents into a chip to process data, you're sending in beams of light. In a lab setting, this works by taking 2 different light sources, light 1 and light 2, and using them as input signals. You can see how these specific wavelengths of light, shown as purple and blue beams, hit the device and trigger distinct, measurable electrical outputs on the monitor. It's computing, sure, but the keystrokes are entirely made of light. How cool is that? Moving on to part 3, the BiOI TiO2 breakthrough. To actually make this work, scientists had to design a material that doesn't even exist in nature. They created a heterojunction, which is basically a customized intersection between 2 very different materials. Specifically, they layered 2-dimensional bismuth oxide, or BiOI, nanoflakes onto a titanium dioxide, or TiO2, thin film. Now, normal materials only let traffic flow one way, which really limits what they can process. But think of this new customized intersection like a highly sensitive traffic cop for electrons. It can dynamically change the flow of traffic depending on exactly who's approaching. Making this dynamic material required a pretty clever chemical trick, and the secret ingredient here is actually glycerol. Let's walk through how this changes the recipe. Step 1. Researchers introduce glycerol to the solution. Because glycerol is super viscous, meaning it's really thick and sticky, step 2 involves a purposefully limited diffusion rate. It essentially slows the whole reaction down. And this slow rate is critical for step 3 because it forces the oxidation of iodine into iodine precipitates. Finally, step 4. What does that actually achieve? Well, it creates an iodine-deficient bismuth-rich material. That perfectly turns the energy band structure of the device so it can act just like that traffic cop we were talking about. And this perfectly tuned material has a literal superpower, a wavelength-controlled bipolar photoresponse. Look, standard diodes in electronics, they're one-way streets. But this heterojunction is a two-way street that changes direction based on the actual color of light hitting it. When it gets hit with invisible ultraviolet light, it creates a negative photocurrent. But when hit with visible light, it instantly switches polarity and creates a positive photocurrent. This switching is the result of a microscopic tug-of-war at the barrier of those 2 materials. It's this delicate balance between electrons recombining and electrons magically passing straight through the physical barrier, which is a quantum effect known as carrier tunneling. That takes us to part 4, 5 gates, 1 device. Let's see how this all builds into an actual working computer processor. Because this material can flow current in 2 different directions based on light, it can do something traditional electronic logic gates just can't easily do. Take a look at this breakdown. To perform an AND gate operation, the device needs both a 365 nanometer UV light and a 475 nanometer visible light at the exact same time. But for a NOT gate, it only requires the 475 nanometer input and no UV light at all. By carefully manipulating the bias voltages and using these UV invisible lights as inputs, researchers proved this single tiny device can successfully perform 5 distinct logic operations, AND, OR, NAND, NOR, and NOT. Doing all of that on one single component, that is a massive leap for reconfigurable computing. Finally, part 5, seeing like a bee. To prove how practical and incredibly powerful this dual-band UV and visible light processing really is, the researchers looked to the natural world. Bees have a biological superpower of their own. When they look at a flower, like these chrysanthemums, they don't just see the blue and purple petals that we see. They perceive ultraviolet nectar guides. These are hidden, glowing patterns on the flower petals that act like landing strips, pointing directly to the food, and they are completely invisible to the human eye. So, by harnessing the UV and visible logic functionality of their new BiOI TiO2 device, the researchers successfully simulated this exact bee vision phenomenon. They achieved what's called biomimetic in-sensor image processing. This is absolutely crucial. The sensor itself is actually doing the thinking, just like a biological eye, rather than just capturing an image and sending it off to a separate, bulky computer brain to be deciphered. They literally use their light-powered chip to process images of flowers in a way that detects and highlights those invisible UV nectar guides directly on the hardware itself. This is just a truly incredible breakthrough. It flawlessly bridges pure chemistry, high-speed computer logic, and biomimicry. This was all recently detailed in the journal Nano Research, and it represents a major, triumphant step forward, not just for computing, but for the future of smart agriculture and environmental imaging, where seeing way beyond the visible spectrum is critical. As the researchers themselves state, these results demonstrate the potential of BiO/TiO2 devices as innovative components for reconfigurable OELGDs. What this really means for us is that these optoelectronic logic gates aren't just theoretical anymore. They're highly tunable, they are incredibly fast, and they're fully capable of replacing the heat-generating electronic gates that are currently holding our tech back. I'm going to leave you with this thought to ponder today. We started by looking at a physical limitation in traditional computers, and we ended up simulating the eyes of an insect on a microscopic chip. The intersection of nature and next-generation computing is really just getting started. If we can build computer chips that see the invisible world just like a bee, what other hidden biological secrets might our future technology unlock? Thanks for joining me on this explainer, and keep asking questions about the hidden worlds around you.